In this final section, we're going to take a look at some AP style problems. AP Solubility Free Response 1. Silver chromate dissociates in water according to this equation. Silver chromate solid into silver ions and chromate ions with a Ksp value of 2.6 times 10 to the minus 12 at 25 degrees C. A. Write the equilibrium constant expression for the dissolving of silver chromate. B. Calculate the concentration in moles per liter of silver ion in a saturated solution of silver chromate at 25 degrees C. C. Calculate the maximum mass in grams of silver chromate that can dissolve in 100 milliliters of water at 25 degrees C. D. A 0.1 mole sample of solid silver nitrate is added to a 1 liter saturated solution of silver chromate. Assuming no volume change, does chromate concentration increase, decrease, or remain the same? Justify your answer. Part A, write the equilibrium constant expression for the dissolving of silver chromate. So Ksp is the silver ion concentration squared, with 2 here, multiplied by the chromate ion concentration. Now let's calculate the silver ion concentration in a saturated silver chromate solution. So initially we have no silver and no chromate. As equilibrium is established, we have a change of 2x for the silver again. So we have a 2 coefficient here, an x for the chromate, so that at equilibrium, we have an amount of 2x for the silver and x for the chromate. And we can set our equilibrium expression equal to the Ksp because that's what it is at equilibrium, right? In a saturated solution, we would expect the reaction quotient to equal the Ksp. So we set it equal to Ksp and substitutes our x for chromate and 2x for silver, so x times 2x squared. We can solve for x. X is the chromate ion concentration. We get 8.7 times 10 to the minus 5. We need to double that to solve for silver at that equilibrium point. We get 1.7 times 10 to the minus 4 molar. Part C, calculate the maximum mass in grams of silver chromate that can dissolve in 100 milliliters of water. The concentration of the silver chromate that dissolved in part B is the same as X, right? Because remember that for every silver chromate formula unit that dissolves, we get 2 silver ions and 1 chromate ion. And the chromate ion concentration at equilibrium was X. Okay, so if the concentration of chromate at equilibrium in a saturated solution is X, that means that's also the concentration of silver chromate that dissolved. Okay, so I can take that X value, 8.7 times 10 to the minus 5, and multiply it by the molar mass of the silver chromate, and we get 331.7 is the molar mass. So that mass is 0.029, that's grams per liter. And then in 100 milliliters of water, so multiply by 0.1 liters, and we get 0.0029 grams. 0.0029 grams. Part D. A 0.1 molar sample of solid sodium nitrate is added to a 1 liter saturated solution of silver chromate. Assuming no volume change, does the chromate ion concentration increase, decrease, or remain the same? So we already have a saturated solution, which means that we start out initially, Q is equal to K, right? If we add solid sodium nitrate, what are we doing? We're adding a source of silver ions. So we're going to increase the concentration here, right? And at that point, we have more product, and we would expect the reaction to shift to the left by Le Chatelier's principle. At this point, Q is greater than K, so we would expect to see some of this silver chromate will precipitate, right, until the equilibrium is reestablished. And in doing so, we have to use some of this chromate ion to form the precipitate. So the chromate ion concentration will decrease. Adding silver ion makes Q greater than K. To reestablish the equilibrium, the reaction shifts from right to left, decreasing Q and using up some of that chromate ion. AP solubility free response 2. In a saturated solution of Ag3PO4 at 25 degrees C, the concentration of silver ion is 5.3 times 10 to the minus 5 molar. The equilibrium constant expression for the dissolving of silver phosphate in water is Ksp equals concentration of the silver ion to the third power times the concentration of the phosphate ion. A. Write the balanced equation for the dissolving of silver phosphate in water. B. Calculate the value of Ksp for silver phosphate at 25 degrees C. C. A 1.00 liter sample of saturated silver phosphate solution is allowed to evaporate at 25 degrees C to a final volume of 500 milliliters. What is the silver ion concentration in the solution? Justify your answer. Part A asks us to write the balanced equation for the dissolving of silver phosphate in water. So if we have silver phosphate solid in water, we have an equilibrium that exists between the silver ions in solution and the phosphate ions in solution. Keep in mind that there are 3 Ag+1 ions for every 1 phosphate 3- ions. Part B, calculate the value of Ksp for silver phosphate at 25 degrees C. So we can start with the given Ksp expression here. And we're told that the concentration of the silver ion in the solution is 5.3 times 10 to the minus 3 molar. And we can use what we know here about the dissolution of the silver phosphate in water to help us find the phosphate ion concentration. So for every 1 phosphate ion, there are 3 silver ions. So the phosphate ion concentration then is 1/3 the silver ion concentration. So 5.3 times 10 to the minus 5 moles of silver per liter times 1 mole of phosphate per 3 moles of silver gives us 1.8 times 10 to the minus 5 molar phosphate ion. We can substitute those two values in to our Ksp expression. So silver, let me just pick a different color here, is 5.3 times 10 to the minus 5 cubed. And then the phosphate is the 1.8 times 10 to the minus 5. Okay, so we get a value of Ksp equal to 2.6 times 10 to the minus 18. In part C, we're told that the solution that starts at 1 liter is allowed to evaporate to half its original volume to 500 milliliters. And we're asked then what happens to the silver ion concentration. And the answer is nothing. The silver ion concentration is still 5.3 times 10 to the minus 5 molar. The silver ion in a saturated solution of silver phosphate is independent of the volume of the solution. AP solubility free response 3. Several reactions are carried out using silver bromide, a cream-colored silver salt that has a solubility product constant, Ksp, of 5.0 times 10 to the minus 13. A, write the expression for the Ksp of silver bromide. B, calculate the value of silver ion concentration in 50 milliliters of a saturated solution of AgBr. C, a 50 milliliter sample of distilled water is added to the solution described in part B, which is in a beaker with some solid silver bromide at the bottom. The solution is stirred and equilibrium is reestablished. Some solid silver bromide remains in the beaker. Is the value of the silver ion concentration greater than, less than, or equal to the value you calculated in part B? Justify your answer. D, calculate the minimum volume of distilled water in liters necessary to completely dissolve a 5.0 gram sample of silver bromide solid. The molar mass of silver bromide is 188 grams per mole. E, a student mixes 10 milliliters of 1.5 times 10 to the minus 4 molar silver nitrate with 2.0 milliliters of 5.0 times 10 to the minus 4 molar sodium bromide and stirs the resulting mixture. What will the student observe? Justify your answer with calculations. F, the color of another salt of silver iodide solid, is yellow. A student adds a solution of silver iodide to a test tube containing a small amount of solid cream-colored silver bromide. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. Write the chemical equation for the reaction that occurred in the test tube. Which salt has the greater value of Ksp, silver bromide or silver iodide? Justify your answer. In part A, write the expression for Ksp of silver bromide. So first, the dissociation equation of silver bromide solid into its ions Ag+1 and Br-1. The solubility product constant only takes into account the aqueous ions. So Ksp with a value of 5.0 times 10 to the minus 13, which was given, is equal to the silver ion concentration multiplied by the bromide ion concentration. B, calculate the value of silver ion concentration in 50 milliliters of a saturated solution of AgBr. So if the solution is saturated, then if we think about this as our ice table for Ag plus and Br minus, initially none is dissolved, and then some dissolves, right, to reach the equilibrium. So that at equilibrium, at this point of saturation, we have X and X, right? And so we can solve for X. We can set our Ksp equal to, if both of these concentrations are X, it would be X squared, which means that X is the square root of Ksp. This is the square root of Ksp, which is our X. And remember that X is both our silver ion concentration and our bromide ion concentration. Here we just need the silver ion concentration, but it is 7.1 times 10 to the minus 7 molar. C, a 50 milliliter sample of distilled water is added to the solution described in part B. So to that saturated solution, we add 50 milliliters of water. It's in a beaker with some solid silver bromide at the bottom. The solution is stirred and equilibrium is reestablished. Some solid silver bromide remains in the beaker. Is the value of silver ion greater than, less than, or equal to the value you calculated in part B? Justify your answer. Since there is still solid at the bottom after adding the distilled water, so after we stir, there's still some solid left at the bottom, even after the equilibrium is reestablished, that means it is a saturated solution. Both the solution in part B and the solution in part C are saturated. Hence, the value of silver ion after the addition of distilled water is equal to the same as we found in part B, 7.1 times 10 to the minus 7 molar. The concentration of ions in solution in saturated equilibrium with a solid does not depend on the volume of the solution, so the molar solubility is constant. As long as the solution is saturated, evidenced by the solid remaining, the ion concentration will be the same. D. Calculate the minimum volume of distilled water in liters necessary to completely dissolve a 5-gram sample of silver bromide solid. The molar mass of silver bromide is 188 grams per mole. So the first thing I did was found the moles of silver bromide. I took 5 grams, divided it by 188 grams per mole, and it's 0.027 moles. We saw in part A that silver bromide evenly dissociates into 2 ions, silver and bromide, in a 1-to-1 ratio. So if 0.027 moles of silver bromide is what dissolves, it's going to dissolve into 0.027 moles of silver and bromide. So our concentration for silver and bromide, 0.027 moles per liter. Our Ksp is equal to silver ion concentration, 0.027 moles per some volume. I didn't put liters here because we don't know the volume. It's the same for bromide. Set that equal to the Ksp, and now we just have to solve for V. So 3.8 times 10 to the 4th liters. So that's a lot, right? 38,000 liters of water is what would be required to dissolve a 5-gram sample of silver bromide. So it's not very soluble. E. A student mixes 10 milliliters of 1.5 times 10 to the minus 4 silver nitrate with 2 milliliters of 5.0 times 10 to the minus 4 molar silver bromide and stirs the resulting mixture. What will the student observe? Justify your answer with calculations. So the first thing I'm doing is finding the moles of silver and the moles of bromide. So 0.010 liters is this 10 milliliters. Just use the colors here, 10 milliliters of 1.5 times 10 to the minus 4 molar silver is 1.5 times 10 to the minus 6 moles of silver ion. And 2 milliliters, so 2 times 10 to the minus 3 times 5.0 times 10 to the minus 4 molar gives us 1 times 10 to the minus 6 moles of bromide. And the total volume, 10 milliliters plus 2 milliliters, is 12 milliliters or 0.012 liters. All right, let's finish this up on the next slide. Once we know the moles of each ion, bromide and silver, and the total volume, we can find the concentration of bromide ion and silver ion after the solutions combine. Use those concentrations to calculate Q, concentration of silver times the concentration of bromide, and we get 1.0 times 10 to the minus 8. So in this case, Q is greater than Ksp, and when that happens, precipitation will occur, right? The equilibrium will shift to the left. Precipitation will occur, and silver bromide will precipitate as a cream-colored solid. F. The color of another salt of silver, silver iodide, is yellow. A student adds a solution of silver iodide to a test tube containing a small amount of solid cream-colored silver bromide. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. Write the chemical equation for the reaction that occurred in the test tube. Which salt has the greater value of Ksp, silver bromide or silver iodide? Justify your answer. Okay, so we start with cream-colored silver bromide in the test tube. So you see they have silver bromide in the test tube and a solution of sodium iodide, so aqueous sodium iodide. And it goes from cream to yellow, which means that we must end with the sodium iodide solid, yellow. Right, so this is cream. And this is yellow. Right? And then we're left with sodium bromide in the solution. So we can separate the aqueous into its ions. And we can eliminate our spectator ion, our sodium, and we get this net ionic equation. And what we precipitate out is this solid yellow-colored silver iodide. In the second part, we're asked which salt has the greater value of Ksp, silver bromide or silver iodide. The Ksp of silver bromide is greater than the Ksp of silver iodide because in the presence of both bromide and iodide ions, the less soluble silver iodide is what precipitated. AgBr has a greater Ksp value as less silver bromide precipitated and more dissociated into ions. Ksp is directly proportional to the amount of ions produced. So silver bromide had more ions, more dissolved than silver iodide because it has a greater Ksp value. And then as a result, the silver iodide is what we saw precipitate out. Another way to think about it is the salt with the lower Ksp precipitated in this case. So silver iodide is less than silver bromide. AP Solubility Free Response 4. A student knows from their solubility rules that silver chloride should have very limited solubility in water at 25 degrees Celsius. To test this, they plan to add 10.000 grams of silver chloride to a beaker with 1.0 liter of distilled water. Then they plan to filter the mixture and collect the undissolved silver chloride and expect it to be only slightly less than the original mass amount. They carried out the experiment and collected these data. Mass of filter paper, 2.3411 grams. Mass of filter paper and collected silver chloride, 12.3385 grams. A. What is the molar solubility of silver chloride? B. What is the Ksp of silver chloride? C. How would the calculated value of Ksp be different if the student used tap water, which contains chloride ions, instead of distilled water? Explain. D. If lead chloride was used instead of silver chloride, what is the expected mass of the filter paper and collected lead chloride if the Ksp of lead chloride is 1.7 times 10 to the minus 5? Part A. What is the molar solubility of silver chloride? So first, let's calculate the grams of silver chloride collected by subtracting the filter paper mass from the total mass collected. We get 9.9974 grams. The insoluble silver chloride, the precipitate that was collected, is not dissolved within the water, so it is caught by the filter paper. The mass of the dissolved silver chloride is equal to the original mass of the silver chloride minus the mass of the precipitate. So originally, we added 10.000 grams. We subtract 9.9974 grams, and that means 0.0026 grams of silver chloride dissolved. Convert this value to the moles of silver chloride to calculate the molar solubility. So the molar mass of silver chloride, 143.32. So we get 1.81 times 10 to the minus 5 molar. Part B, what is the Ksp of Agcl? The equilibrium equation for silver chloride is silver chloride solid, dissociates into silver ions and chloride ions in a 1-to-1 ratio. The solubility product constant, Ksp, only takes into account the aqueous ions. So Ksp equals silver ion concentration times chloride ion concentration. In part A, we calculated the molar solubility of silver chloride as 1.81 times 10 to the minus 5 molar. Since the silver ion to chloride ion ratio is 1-to-1, those two concentrations will be equal at equilibrium and equal to the molar solubility because they're in a 1-to-1 ratio in the lowest molar ratio to the original solid silver chloride. So Ksp is just 1.81 times 10 to the minus 5 times 1.81 times 10 to the minus 5. So we get a Ksp value of 3.35 times 10 to the minus 10. C. How would the calculated value of Ksp be different if the student used tap water containing chloride ions instead of distilled water? Explain. Since tap water is ionized and contains common ions with Agcl, so we have a common ion, right? We got to think about what's the effect of a common ion. The common ion effect lowers the molar solubility and lowers the Ksp. Increases in initial amounts of chloride in the beginning of the experiment will cause the equilibrium to shift left, causing more solid to precipitate out. Less ions would be present in the solution phase. Solubility decreases due to the common ion. So we would expect a lower solubility and therefore an even smaller value of Ksp to be calculated. D. If lead-2 chloride was used instead of silver chloride, what is the expected mass of the filter paper and collected lead-2 chloride if Ksp of lead-2 chloride is 1.7 times 10 to the minus 5? So let's find the molar solubility from the given Ksp value. The dissociation equation for lead-2 chloride is PbCl2 dissociates into Pb2 plus and 2 chloride minus ions. And the Ksp expression is the concentration of the lead-2 plus ions times the concentration of the chloride ions squared. The Ksp given is 1.7 times 10 to the minus 5. And at equilibrium, the concentration of the lead-2 plus will be X. The chloride ion will be 2X because of the 2 coefficient, and then squared. You can solve for X here. This is 4X cubed. So we need to take this, divide by 4, take the cubed root to solve for X. X is the lead-2 plus ion concentration, and we get 1.62 times 10 to the minus 2. That's also the molar solubility. So 1.62 times 10 to the minus 2 moles of lead chloride would dissolve in 1 liter of water, which is the same volume that we had in part A. Let's find what the mass of that would be. Multiply by the molar mass of lead-2 chloride, and you get 4.15 grams would dissolve in a liter. If the original mass added was 10 grams and 4.51 grams dissolved, we'd be left with 5.49 grams precipitated. And then add that to the mass of the filter paper that was given in part A, and we would get 7.83 grams. That would be the expected mass of the filter paper and the collected lead-2 chloride, which is a significant amount less than for the silver chloride, right? Because more of it dissolved. AP solubility free response 5. The molar solubility of zinc carbonate in distilled water is 1.21 times 10 to the minus 5 molar. A, what is the Ksp for zinc carbonate? B, what is the molar solubility of zinc carbonate in 0.1 molar zinc chloride? C, explain the difference in molar solubilities between the two solutions. D, if the following changes were made to a saturated solution of zinc carbonate in distilled water, explain what would happen. to the concentration of zinc 2+ ions if water was evaporated, the Ksp if water was evaporated, the mole quantity of dissolved ions if additional distilled water was added, and finally the molar solubility of zinc carbonate if an aqueous solution of manganese chloride was added. The Ksp of manganese carbonate is 2.24 times 10 to the minus 11. A, what is the Ksp for zinc carbonate? The dissociation equation is given, or we can write it as zinc carbonate solid dissociates into zinc 2+ ions and carbonate 2- ions. There's a 1-to-1 ratio of ions here. So Ksp is just the concentration of zinc 2+ times the concentration of carbonate. And then we're told that the molar solubility is 1.21 times 10 to the minus 5 molar. And since it's a 1-to-1-to-1 ratio of zinc carbonate solid to zinc ions to carbonate ions, that molar solubility is also the equilibrium concentration for the zinc 2+ ions and the carbonate ions. So we get a Ksp of 1.46 times 10 to the minus 10. B, what is the molar solubility of zinc carbonate in 0.1 molar zinc chloride? So at equilibrium, we're not in distilled water anymore, right? We're in a solution that has a common ion. That common ion is the zinc ion. And at equilibrium, the zinc ion concentration will be 0.1. And we can use that 0.1 at equilibrium because it's so much larger than the Ksp value that we found on the previous slide. That little zinc would be contributed from the zinc carbonate. So remember that we can say that initially we have no chloride ion, but we're in a solution of zinc carbonate, which contributes some zinc. And then the change, as any dissolving of the zinc carbonate occurs, would be X for each of the ions. And so at equilibrium, we'd have 0.1 plus X for zinc and X for, oh, it's not supposed to be chloride, it's carbonate, excuse me. And so what we're saying is this change relative to this very large concentration is so small that we can assume at equilibrium the concentration of the zinc ion is 0.1. And we don't know the carbonate ion concentration, but we can find it. Okay, we can find it. We know the Ksp from the previous slide, 1.46 times 10 to the minus 10, is equal to the zinc ion concentration times the carbonate ion concentration, which we don't know. We solve for it, we get 1.46 times 10 to the minus 9, and that is also the molar solubility, right? Because for every X zinc carbonate that dissolves, we get X carbonate ions. So we get 1.46 times 10 to the minus 9 molar. Explain the difference in molar solubilities between the two solutions. So in water, the molar solubility was 1.21 times 10 to the minus 5 molar. And in zinc chloride, the molar solubility was 1.46 times 10 to the minus 9. Okay. In distilled water, the molar solubility is greater than in zinc chloride. Why? Because in zinc chloride, we have this zinc 2+ ion that acts as a common ion in the solution, and that shifts the equilibrium to the left, resulting in fewer dissociated ions, which contribute to the molar solubility. D, if the following changes were made to a saturated solution of zinc carbonate in distilled water, explain what would happen to part 1, the concentration of the zinc ions if water was evaporated. Nothing would happen to the concentration of the zinc ions. The equilibrium would simply shift left to dissipate the higher concentration created by the evaporation of water. Since the solution remains saturated, the ratio of the zinc ions and water left over is still constant, and therefore it's the same concentration. D. If the following change were made to a saturated solution of zinc carbonate in distilled water, explain what would happen to the Ksp if water was evaporated. Nothing would happen to the Ksp. We just finished saying in part 1, remember that Ksp is the concentration of zinc and carbonate, and we just finished saying that the concentration of the zinc would remain the same, and therefore so would the carbonate, because the solution would remain saturated. It would just shift the equilibrium, right, to account for the decrease in the water. And if nothing happens to the concentrations, then nothing happens to the Ksp either. The reaction will shift to a new equilibrium position, but the Ksp would be unaltered since the ion ratio remains the same in the still saturated solution. Ksp will only be altered by temperature change. D. If the following changes were made to a saturated solution of zinc carbonate in distilled water, what would happen to the part 3 mole quantity of dissolved ions if additional distilled water was added? So if we add more distilled water, what happens to the moles of ions dissolved? If we add more water, then the moles of dissolved ions increases. The absolute number of dissociated ions increases since added distilled water allows more zinc carbonate to dissolve. So if I have zinc carbonate in equilibrium with zinc and carbonate ions, and I add more water, I make it so that more ions can dissolve. I can shift that equilibrium to the right, and therefore I'll have more moles of dissolved ions. D. If the following changes were made to a saturated solution of zinc carbonate in distilled water, explain what would happen to the part 4 molar solubility of zinc carbonate if an aqueous solution of manganese chloride was added. If the Ksp of manganese carbonate is 2.24 times 10 to the minus 11. The molar solubility of zinc carbonate increases since manganese carbonate has a lower Ksp. So the Ksp for manganese carbonate is 2.24 times 10 to the minus 11. And we calculated 1.46 times 10 to the minus 10 for the zinc carbonate, Ksp. Okay, so since the manganese carbonate has a smaller Ksp, the solubility of the zinc carbonate would be greater. The manganese ions will preferentially precipitate with the carbonate ions, shifting the equilibrium to the right. Zinc carbonate would have to produce more ions to compensate the manganese carbonate ions. AP solubility free response 6. A student mixes 120.0 microliters of 0.0020 molar calcium nitrate with 80.0 microliters of 0.0040 molar sodium fluoride, expecting to form a precipitate. A. Write the proper net ionic reaction for the expected reaction. B. Predict whether the student should expect to form a precipitate or not. Justify this with the calculation. Ksp for calcium fluoride is 3.45 times 10 to the minus 11. C. Agree or disagree with the following statements and justify your answer. 1. Evaporating water from the mixture makes the precipitate more likely to form. B. The ions remaining in solution in order of increasing concentration are calcium, fluoride, sodium, and then nitrate. D. Given that the Ksp for magnesium fluoride is 3.50 times 10 to the minus 9, what is the Ksp for the reaction given? Magnesium 2 plus ions plus calcium fluoride solid produces calcium 2 plus ions and magnesium fluoride solid. A, write the proper net ionic reaction for the expected reaction. The ions present in solution are calcium, nitrate, sodium, and fluoride. If this reaction were to occur as a double displacement reaction, we would get both sodium nitrate and calcium fluoride as products. Nitrate and sodium compounds are soluble, so sodium nitrate is soluble. So we show that as aqueous. And the solid precipitate is the calcium fluoride compound. Then write the net ionic equation as the formation of the solid calcium fluoride from its ions. So sodium and nitrate are both spectators. We end up with a solid reaction between calcium and fluoride to produce calcium fluoride solid. B, predict whether the student should expect to form a precipitate or not. Justify this with a calculation. Ksp for calcium fluoride is 3.45 times 10 to the minus 11. What we need to do is compare Q, the initial reaction concentrations present, to Ksp to determine whether or not a precipitate will form. To calculate the initial concentrations, find the moles of each calcium ion and fluoride ion, and then find the concentrations in the combined solution. All right, so first, the total volume, 120 microliters, and combined with 80 microliters is 200 microliters total. The moles of calcium, if it's 0.002 molar, so 2.0 times 10 to the minus 3 molar, multiplied by the volume, so 120 microliters is 120 times 10 to the minus 6 liters. That's 2.4 times 10 to the minus 7 moles. So the initial calcium concentration after mixing, 2.4 times 10 to the minus 7 moles over 200 microliters, 200 times 10 to the minus 6 liters, is 1.2 times 10 to the minus 3rd molar. We can repeat that for the fluoride ion. So 0.0040 molar sodium fluoride is 4 times 10 to the minus 3 molar fluoride ion. And multiplied by the volume 80 microliters, 80 times 10 to the minus 6 liters, gives us 3.2 times 10 to the minus 7 moles of fluoride, divided by the total volume, 200 times 10 to the minus 6 liters. So an initial concentration of 1.6 times 10 to the minus 3 molar. Now that we know the initial reaction concentrations present, let's compare Q to Ksp. So we know that the dissociation is calcium fluoride solid into its ions, calcium and fluoride. This is the direction of the Ksp reaction, right? This is how we write our Ksp expression. So Q then is the concentration of the calcium, 1.2 times 10 to the minus 3rd, times the concentration of the fluoride, 1.6 times 10 to the minus 3. We calculated these concentrations on the previous slide. Squared for the fluoride, because we have a 2 coefficient. Q is 3.0 times 10 to the minus 9. Compare that to Ksp, which was given as 3.45 times 10 to the minus 11. In this case, Q is greater than Ksp. So the reaction will shift the equilibrium to the left and a precipitate will form. When Q is greater than Ksp, a precipitate will form. C. Agree or disagree with the following statements and justify your answer. 1. Evaporating water from the mixture makes the precipitate more likely to form. Evaporating water from the mixture makes the precipitate more likely to form by reducing the volume of the mixture. As shown by the red arrows in the calculations, decreasing the volume increases the calcium and fluoride ion concentrations. If these both increase, then Q would also increase, and as Q increases, the reaction becomes more likely to form a precipitate. C. Agree or disagree with the following statements and justify your answer. 2. The ions remaining in solution in order of increasing concentration. So the lowest concentration, calcium, then fluoride, then sodium, and then nitrate would be the greatest. So it is true that nitrate is greater than sodium. So this is true. We can verify it with some calculations. Remember, nitrate and sodium don't participate in the formation of the precipitate here. So we can just find the number of moles of nitrate and the number of moles of sodium initially present, and then find the concentration in the total volume. So we know that we have 0.0020 molar calcium nitrate in 120 microliters. So you see here that for every 1 mole of calcium nitrate, we'd have 2 moles of calcium. So that's why here I have 4 times 10 to the minus 3rd molar nitrate ion initially in 120 microliters, or times 10 to the minus 6 liters of water. So that the moles of nitrate are 4.8 times 10 to the minus 7 moles. In the total volume of 200 microliters, or 200 times 10 to the minus 6 liters, we get 2.4 times 10 to the minus 3 molar nitrate. And then for sodium, we've seen this calculation before. 0.0040 molar sodium ion in 80 microliters, or 80 times 10 to the minus 6 liters. 3.2 times 10 to the minus 7 moles of sodium in a total volume of 200 microliters, or 200 times 10 to the minus 6 liters. It's 1.6 times 10 to the minus 3 molar sodium. So we can see that the sodium is less than the nitrate. So this is correct. Sodium is less than the nitrate. In part B, there are more ions of fluoride than calcium present in the solution. But since 2 moles of fluoride are required to react with every 1 mole of calcium, right, in order to form this. Remember, there's 2 moles of fluoride for every mole of calcium. Fluoride is the limiting reactant, so there will be a smaller concentration at equilibrium. So the order given here is incorrect because the fluoride ion concentration is less than the calcium ion concentration. So we had found that initially there was 1.2 times 10 to the minus 3 molar calcium ion and 1.6 times 10 to the minus 3 molar fluoride ion. Okay, so if you just went based off of that, this would be correct, right? There are more calcium ions, more fluoride ions than calcium ions, right? 1.6 versus 1.2. So calcium is less than fluoride. But fluoride is limiting, right? Because this is the precipitate that's forming. So there will be a smaller concentration at equilibrium. D, given that the Ksp for magnesium fluoride is 3.5 times 10 to the minus 9, what is the Ksp for the reaction given? Magnesium 2 plus calcium fluoride produces calcium 2 plus magnesium fluoride. Let's write the 2 net ionic equations that sum to the above reaction. The first is calcium fluoride dissociating into its ions, calcium and fluoride. We have a Ksp for that already that we've calculated. And the second is the magnesium ions plus the fluoride ions producing this solid magnesium fluoride solid. Okay, and this would be the inverse of the Ksp for magnesium fluoride. And it's the reverse of how we write a Ksp. When the two equations are added, when you add 2 equations together, you multiply their equilibrium constants. Since the magnesium fluoride reaction occurs in the opposite direction of dissociation, the inverse of its Ksp is used. So the overall Ksp is the Ksp for the calcium fluoride, this one, multiplied by the inverse of the Ksp for the magnesium fluoride. So the Ksp for the calcium fluoride from earlier, 3.45 times 10 to the minus 11, divided by the Ksp for the magnesium fluoride, 3.5 times 10 to the minus 9, gives us an overall Ksp of 9.86 times 10 to the minus 3. AP Solubility Free Response 7. A student mixes 4.5 milliliters of 0.0020 molar sodium hydroxide with 4.5 milliliters of 0.0010 molar cadmium 2 nitrate, expecting to form a precipitate. A. Write the proper net ionic reaction for the expected reaction. B. Predict whether a precipitate will form. Justify this with a calculation. Ksp for cadmium hydroxide solid is 5.3 times 10 to the minus 15. C. Agree or disagree with the following statements and justify your answer. 1. Increasing the volume of the solutions added will make the precipitate more likely to form. 2. Increasing the concentrations of the solutions added will make the precipitate more likely to form. 3. Draw a picture representing the relative amounts of ions left in solution after the solutions have been mixed. D. Given that the Ksp for cadmium oxalate CdC2O4 is 1.4 times 10 to the minus 8, what is the K for the reaction below, where we have cadmium hydroxide, oxalate ion, producing hydroxide ions, and cadmium oxalate solid. Part A, write the proper net ionic reaction for the expected reaction. If the reaction occurs as a double replacement reaction, the products are sodium nitrate and cadmium hydroxide. Sodium nitrate is soluble, so it will not form a precipitate. Therefore, the expected precipitate is cadmium hydroxide. So we have cadmium hydroxide solid produced from its ions cadmium 2 plus and 2 hydroxide ions. B, predict whether a precipitate will form. So what we need to do is compare Q with the initial reaction concentrations to Ksp to determine whether or not a precipitate will form. First, find the moles of cadmium and hydroxide initially present, and then find the concentrations in the combined solution. The total volume is the sum of each of the individual 4.5 milliliter solutions, so 9 milliliters. The moles of cadmium are the concentration, 1 times 10 to the minus 3 molar, multiplied by the initial volume, 4.5 times 10 to the minus 3 liters, 4.5 times 10 to the minus 6 moles. So the concentration in a total volume of 9 milliliters, or 9 times 10 to the minus 3 liters, is 5.0 times 10 to the minus 4 molar. Repeat this for the hydroxide. 0.0020 molar, or 2 times 10 to the minus 3 molar, in 4.5 milliliters, or 4.5 times 10 to the minus 3 liters, is 9 times 10 to the minus 6 moles. In 9 milliliters is 1.0 times 10 to the minus 3 molar hydroxide. Now that we know the initial concentrations, let's calculate Q. So Q is the concentration of the cadmium ion times the concentration of the hydroxide ion squared. Right? Same as the Ksp, but using initial concentrations. So let's substitute those concentrations. 5.0 times 10 to the minus 4 times 1.0 times 10 to the minus 3 squared. Q is 5.0 times 10 to the minus 10. Ksp given 5.3 times 10 to the minus 15. Q is greater than Ksp, so the reaction will occur in the direction that forms a precipitate. C. Agree or disagree with the following statements and justify your answer. 1. Increasing the volume of the solutions added will make the precipitate more likely to form. Increasing the volume of solutions added will not make precipitate more likely to form. The Concentrations will not change, which is what the Q and Ksp values are dependent on. 2. Increasing the concentration of the solutions added will make the precipitate more likely to form. Increasing the concentration of solutions will increase the Q value, making the reaction more favorable in the direction of forming more precipitate. 3. Draw a picture representing the relative amounts of ions left in solution after the solutions have been mixed. Using the initial amounts, determine the number of moles of sodium and nitrate present, as they do not form products after they dissociate. The calculations show that the number of moles is the same for each ion. So given the initial concentration of sodium and the initial volume, we get 9 times 10 to the minus 6 moles. The same for nitrate, but notice we've doubled it because there are 2 nitrate ions that dissolve for every cadmium nitrate. And we get 9 times 10 to the minus 6 again. So based on stoichiometry and the number of ions in solution, there are no cadmium or hydroxide ions present as they are used in forming the precipitate. So let me show you what I mean by that. We had calculated the cadmium concentration to be 1.2 times 10 to the minus 3. No, 5.4. I was looking at the wrong one. 5.4 times 10 to the minus 5.0 times 10 to the minus 4. And the hydroxide ion concentration to be 1 times 10 to the minus 3. Okay. And 2 of these will react for every 1 of these. And the ratio of, if I double this, I get 2 times 10 to the minus 3. And the ratio here is 4 to 1. So this will precipitate or form exactly 4 molecules of cadmium hydroxide, or the ratio is 4. And so no excess cadmium or hydroxide ions are remaining. Okay, so based on the stoichiometry and the number of ions in solution, there are no excess cadmium or hydroxide ions present as they're used in forming the precipitate. D. Given that the Ksp for cadmium oxalate is 1.4 times 10 to the minus 8, what is the K for the reaction below? Ksp for cadmium hydroxide is 5.3 times 10 to the minus 15. So here's the reaction. Let's just write these 2 net ionic equations. We have cadmium hydroxide separating into its ions, hydroxide and cadmium. And then we have cadmium ion and oxalate ion producing cadmium oxalate. So this is written as the Ksp for the cadmium hydroxide. Okay. And this is the inverse of the Ksp for cadmium oxalate. Okay. And so we just multiply the Ksp values when we add together. And so we take the Ksp of cadmium hydroxide, 5.3 times 10 to the minus 5, multiply by the inverse of the cadmium oxalate Ksp, and we get 3.78 times 10 to the minus 7 as our overall value of K.